Hi everyone, I have a problem and I want to simulate a shell and tube heat exchanger. I have two stream, cold and hot. The hot stream is ethylene glycol C2H6O2. The inlet temperature is 317 Kelvin and the pressure inlet is 3 atmosphere. Also the temperature outlet temperature is 350 Kelvin. Also I have a cold stream as R12, which is difluoromethane CCl2F2 at flow rate of 12,000 kg/h, and the temperature inlet is 250 Kelvin and the pressure inlet is 8 atmosphere. Also the temperature outlet for cold stream is 300 Kelvin. In order to simulate a shell and tube heat exchanger, it is required to have duty as a spec for shortcut method. So I'll go to simulation environment. First of all, I have chosen the components before and chose the NRTL method. So I'll go to simulation method, simulation environment. First of all, in exchanger, I use a heater. And rename it to heater and make it a little larger, and material, inlet and outlet, I'll rename it to R12 and R12 out. R12 in and R12 in, R12 out. It is something here. Okay, for R12 in, I enter the temperature. First of all, I alter the unit set to metric. So for R12 mass fraction, and this goes to 0, it is to 12,000 kilogram. The total mass basis is mass, kg/h. The temperature is 250 Kelvin and the pressure is 8 atmosphere. I'll be back to flow sheet. The composition, mass fraction as base, and the temperature is 300 Kelvin and we have no pressure drop, and the pressure for outlet R12 is 8 atmosphere. Total flow basis is mass and it is 12,000 kg/h. So I'll be back to main flow sheet and blocks. We should enter two spec for heater. The temperature change, for example, the temperature change between inlet stream and outlet stream, as you see from the problem. The inlet stream is 250 Kelvin and the outlet stream is 300 Kelvin, and the delta T is 50 Kelvin. The pressure, the delta pressure for the value for pressure, if I want to set the pressure for outlet, I should enter a positive value, but if I enter a negative value, it means that this value is pressure drop, and the valid phases for heater is vapor liquid. So I reinitialize the simulation and run it. It takes some seconds. Results are available. Okay, I'll go to this part, this panel, results summary. Heater, the streams are in or out. Okay, results. As you see from this window panel, the temperature outlet is 300 Kelvin. Outlet pressure is 7.9 atmosphere. As you see, the delta P is 0.1, and the heat duty as kilowatt is 153.5. Okay, I use it to simulate the shell and tube heat exchanger as a spec. I'll go to main flow sheet. Here we have some kinds of heat exchangers, but the shell and tube heat exchanger is here. We have two types, Gen HT and Gen HS. Gen HS means the stream enters the tube side, and the Gen HS means the hot stream enters the shell side. So I want to use this form, rename it to heat X and make it some larger. The streams, as you see, when I close the plus to this sign, to this part, it shows the cold required stream, and I rename it R12 out, R12. Okay, I should cold out and cold in. Another stream is for hot stream. I assign it to the exchanger and rename two streams, hot in and hot out, or I can rename it to EG in and EG out. Okay, I go to cold in. The temperature is 250 Kelvin and the pressure is 8 atmosphere. Total flow basis, mass, and 12,000 kilogram per hour, and the value for composition R12 is 1, Ag 0 as mass fraction. Go to main flow sheet, cold out. The temperature is 300 Kelvin, and the pressure we don't consider any pressure drop, so we assign 8 atmosphere. Total flow basis is mass, and total flow rate is 12,000 kilogram per hour, and the composition is mass fraction 1 and 0. Okay, I'll be back to main flow sheet. Ethylene glycol in as hot stream. The hot stream 370 Kelvin T in, and P in 3 atmosphere. I should set this temperature and pressure. Okay, total flow basis is mass and total flow rate. I assume the total flow rate for ethylene glycol 5,000 kilogram per hour. It's an assumption, and I can change it according to the specification of my problem. EG1 and R12 0 mass fraction. Okay. So I'll be back to flow sheet. Heat X, the shortcut method for the specification of shell and tube heat exchanger. The shortcut method is used. The calculation mode is designed. I don't use the rating because I don't have any geometry of the heat exchanger, and I want to set a geometry for my heat exchanger. The exchanger specification can be many different choices. Hot stream outlet temperature decrease, or hot outlet cold inlet temperature difference, and the other ones. But the spec that I had determined is exchanger duty, and the value for this specification is 153.554 kilowatt. Okay, it's the blue circle with white sign, so that's enough. I can reinitialize or reset my simulation and run the simulation for the first one. Results are available. I can go to stream summary. Okay, stream summary. Cold in, cold out. Ethylene glycol in, ethylene glycol out. As you see from this point, the temperature of ethylene glycol out is 325, and it is much far from our spec 350. So in order to set it to 350, I should go to main stream, and I will alter it to 4,500 kilogram per hour, and reset the simulation again and run it again. The results are available. A stream summary. Okay, the temperature of ethylene glycol out is 320.3, and it is a little more than the spec. So I'll be back to flow sheet. Ethylene glycol 4,100 kilogram per hour. I reset it for a third time, and I'll run the simulation. Results are available with no errors. The stream summary, but input change, but I should run again. Okay, the temperature output for ethylene glycol is 350.3, So it's a good spec for me. So I can go to the view, and what can I do to see this part? Okay, activation dashboard and EDR exchanger feasibility. In order to have the geometry of for my heat exchanger, I convert to rigorous, select exchanger type shell and tube, select conversion method size exchanger, specify exchanger geometry. I don't have any geometry. Okay, so I select the size exchanger. If I had an EDR template file, I could choose this one. But for example, for the other examples, I had many EDR template file here. I can show you. I can choose one of them. But in this example, I don't have any template file for my heat exchanger, so I use size interactively. I can convert to this part. It takes some seconds. Okay. The thermotype. We have 3 thermotypes. The first one is for front head of my heat exchanger. We have different front head. A type channel and removable cover. B type bonnet bolted or integral with tube sheet. And C type integral tube sheet and removable bundle. N type integral tube sheet and non-removable bundle. And D type for high pressure enclosure. So I can choose one of these thermotype for my front head of my heat exchanger. I choose B1. And for the middle section of heat exchanger, we have some schematics. For example, E type, it shows 1 pass shell. F type, it shows 2 pass shell with long baffle. G type shows split flow. H type double split flow. J type divided flow with 1 nozzle inlet and 2 nozzle outlet. And I type divided flow nozzles, 2 inlets from the bottom of the heat exchanger and 1 outlet from the top of the heat exchanger. Kettle type, cross flow, these multi-tube hairpin M shell and double pipe. These thermotype middle section schematics are in the standards of TEMA, and you can go through all of them and study about them. The other part is M type for the rear head of the heat exchanger, M bonnet, N type integral channel with flat cover, L type removable channel with flat cover, N type integral channel with flat cover, I said it. P type outside packed floating head, I choose it for my heat exchanger. As I said, the location of hot fluid is in shell side. Also, we can change the tube OD of tube sheet and the pitch. The pitch for tube OD for tube pattern is about 1.25 times according to the standards of the tube OD. Okay. The tube pattern can be 300 triangular, 60 degrees rotated triangular, 90 square and 45 rotated square. If we want to clean the shell size mechanically and with no any chemical materials, it's better to choose the 9 degrees square for our tube sheet. But I choose 3 degrees triangular. We have baffle in our heat exchanger. Okay, baffle type can be single segmental or double segmental. The schematics are here, and also triple segmental or unbaffled. But I use the single segmental for my heat exchanger. And the baffle cut orientation, it can be horizontal or vertical, and I choose horizontal type. According to the fluid that is used in heat exchanger, tube side and shell side, we can choose the material. There are so many different materials here, but I choose the carbon steel material. Okay, I'll go to process tab. The process tab, kilogram per hour, the inlet pressure as atmosphere, and the temperature in Kelvin. The hot side and outside. Hot side, inlet temperature and outlet temperature for hot side is 350 Kelvin. I will choose it. 350 Kelvin. And the cold side, the outlet temperature is 300 Kelvin. Also, we have heat exchanged. We have calculated before. It is assigned here. Allowable pressure drop. It's so important. According to design criteria, we choose the allowable pressure drop. For example, I choose 5 psi for cold side and 3.77 is the default one. And fouling resistance for different fluids in TEMA standards, there are many fouling resistance suggestions. So I set it to 1.00018 for hot side and shell side. The same fouling resistance value is entered. Okay, I've sized my exchanger. Okay, warnings, operation warnings. It shows low cross flow fraction, the optimum design to minimize surface area, a tight baffle pitch with a low cross flow fraction. And the other operation warning is low cross flow fraction in the shell side and high shell baffle leakage fraction. It is the serious warning, and I should eliminate this warning. So in order to eliminate these two warnings, it's better to go to geometry. So I will change the pitch of tube OD to 1.25. Okay, size it again. Warnings. Okay. Default allocation of hot stream. It is not a serious warning, and the sizing of heat exchanger is acceptable. So I accept the design. As you see, I should run it again. Results are available, and this part shows that the summary of the simulation of EDR is okay. Temperature, vibration, ρV2 heat transfer, pressure drop and the others are in green circles, and the summary is okay. If I show this, I'll go to main flow sheet. It shows the heat exchanger as a blue circle. This circle is green. We have no circle here. Okay, and show legend, model statue, and the other ones. Okay, I'll be back to this panel for the results. As you see from the stream results, R in, R out, E in, EG out. We have seen these values before, and the other part that I can show you is the EDR browser. EDR browser shows the geometry, the summary of the geometry. We can see all parts of it. Set process, process data, and set geometry. When it's connected, we can change some parts and some values of this window channel. For example, we can change the for example, we can change the tube passes to 3, input changed, and next button. It calculates. Results are available. Okay, one warning, and it's about the heat transfer. We can see the warning, EDR browser, geometry, process data, warnings. Okay, the warning is the optimum design to minimize surface area is something like this. It has 2 warning about the low cross flow fraction, and it is this changing of the geometry is not appropriate for us. So I'll be back to EDR browser and set the geometry tube passes 2, and we can change the other parts. For example, the number of tubes to 40. When it's in working offline, the changing of the parameter has not affected, so we should go to connected mode. So the input changed, and it's better, it's necessary to the EDR exchanger feasibility be in connected mode. So we have changed the number of tubes, and next, and run the simulation. It calculates. It takes some seconds. Results are available. We go to EDR exchanger feasibility. By changing the number of the tubes, also all the parts are okay, and we see the green circle. Also, we can go to EDR channel EDR browser, or we can change the OD from 0.75 to 1 inch input change, but the EDR exchanger feasibility should be connected, and we run the simulation again. It takes some seconds. Also, it takes some seconds to calculate. We should be patient. Results are available. Okay. Warning. Another warning is for heat transfer. The optimum design to minimize surface area and also the low cross flow fraction. In order to eliminate these two heat transfer warnings, I'll go to EDR exchanger, EDR browser, and okay, again I run the simulation. Okay, calculating the results is available. All the parts are green circles, and we can save EDR browser. We can save it. And it is finished. Thank you for listening to my heat exchanger simulation part.